Okay, gentlemen, I'm going to go ahead and start now. And what we're going to cover today is back in the 90s, they started this process of what was called zero config, where the philosophy was you shouldn't have to configure everything over and over again on devices. In this case, the IP address and subnet mask and default gateway of individual host machine devices. Shouldn't have to configure all that stuff over and over again just because somebody moves a machine from one place to the other. So before then, well, I'll tell you a story. In the early 90s, I was working for a company that I was managing the networks and the servers, and I was responsible for 200 workstations that 200 employees used. And they were always moving and promoting themselves from one office to another office. And now these were Macintosh users mostly. This is a graphics production for a publishing company. And the thing about Macintosh people is, I joked about Macintosh people, they already know everything there is to know about computers. So when they moved their workstation from one office to the new corner office they got promoted to, it was probably in a different floor and it was on a different subnet. They didn't know anything about that. So they just type in whatever numbers they wanted to into their network settings, and then they'd get mad and call me because it didn't work properly. So I would have to keep track of IP addresses and scratch off this number from this floor and add this number to this floor and go up and manually reconfigure the device. So in the mid-90s, when this DHCP, Dynamic Host Configuration Protocol, came out, it would automatically configure the IP addresses of their workstations. So even if they moved to a different floor on a different network, they would automatically be granted a new address that was proper for that particular network. And then as the running out of IP version 4 addresses, our 32-bit addresses, they started realizing that in the mid-90s that there was a crisis, and that's when they came up with IP version 6. And they put a lot of other features in IP version 6, which they then started calling zero config. The idea being, I can plug a bunch of devices together and I just don't have to configure them at all. And they'll just start working automatically. So if you're a cable modem customer, for example, and you buy a Linksys style home router and you plug it into your cable modem device, it'll start working without you having to configure it to do anything at all. You might want to go in and set a password on your Wi-Fi or something, but it should start working automatically. So that's the idea behind zero config. So we're going to look at DHCP, both version 4 for IP version 4, which is the more widely used today, and also for version 6 for IP version 6. And then last, we'll look at the first hop redundancy protocol, which is the idea that if I just have one router and it fails, I'm out of business. If I have two routers, why not set them up so they'll back each other up? That way, if one router fails, we can route all our information through the other router and we can connect to the rest of our networks. So the PowerPoints I'm going to use are listed on the PowerPoint presentations of the My TCC Blackboard, and they're entitled DHCP version 4 better graphics. I'm using one that I think has better graphics than the official one. I have posted the official one, but I'm going to use that one. And then I'm going to use the DHCP older summary one for DHCP version 6. And then we'll go to the actual real official one for module 9 for first hop redundancy protocol. Okay, so let's see. Wait a minute. See, somebody popped in and popped out. Take some attendance. I'm going to share the first PowerPoint slideshow now. So that's going to be share files. And it should be this one. And let's see if this pops up for you guys. Oh, I think I can click this first. There we go. Okay, this is the old chapter scheme. Pay no attention to the chapter number scheme. They changed to modules. So here is the idea that you should be able to, and most universally now, almost all desktop client devices, Windows or Linux or Mac OS, are configured so that out of the box, well, for example, in Windows, if you go into the network control panel, it says something about the button is checked by default that says obtain the IP address automatically. And then you can click the static button, and we've always done static configurations on our workstations and our labs. But we're ready to click the obtain the IP address automatically. And what that means is it tells that workstation to act as a DHCP client and request a DHCP server to grant him an address. So what happens is, first of all, when the client machine boots up, he doesn't have any idea what his IP address should be. He hasn't been told yet. Maybe he moved it. Maybe he was one of those guys at my publishing company that moved to the new corner office on a different floor, and so he actually has to get a different IP address than he got last time. Now, Microsoft machines are pretty arrogant. Microsoft's kind of an arrogant company. Microsoft computers always try to use the same IP address that they used yesterday or last week. But if they're told they're on a new network now, they will grumbling, they'll go ahead and take it and they'll use it. So here's what's happened. The client machine, let me see, am I allowed to do this? So here's our client machine. And he boots up. And even though he's a Microsoft computer, he knew what IP address he used before, he's not allowed to start using it right away. He's got to get it authorized when he boots up again. So he's going to send out a broadcast message. Now, what do we know about broadcast messages? When a broadcast message goes into an Ethernet switch, it's compelled to flood it at all the other ports. So guaranteed, even though this client machine does not yet have an IP address, the broadcast is going to flow into the switch, and the switch is going to go ahead and flood that broadcast to the server. So that's a DHCP Discover broadcast sent out by the client workstation. The DHCP server will then hear that message, and he'll say, oh, yeah, I'm a DHCP server. It's port 67, port 68. Yeah, it's coming in on the right channel. And he'll send back an offer message. Now, Microsoft recommends that you have 2 or more DHCP servers, because what if one of them crashes? Well, that's the thing about Microsoft servers. Yeah, they crash all the time. So you should have a backup server there. It's kind of like the same thing with the Microsoft domain controllers. You should have a backup domain controller and a primary domain controller, or what they call it now, they call them domain controllers or replica domain controllers, so they can back each other up when everybody comes to work in the morning and starts logging in. So the DHCP server hears the broadcast request and he sends back an offer. If there were 2 DHCP servers, or maybe more, they both may hear the message and they both may send an offer. The client may hear 2 offers. He's going to try to accept the one that he used last time, if it was the case that he used one time before. So let's just say in this case it's a simple network with only one DHCP server. He hears the client machine hears the one DHCP offer, and he says, okay, well, let's say it was 2. Let's say he heard 2 DHCP offers. He's going to pick the one and say, I like your offer the best on that first DHCP server, and I accept it. And the other DHCP server never hears that request, and he says, well, he doesn't want me, then I'll let the other guy take care of him. So the last act of the DHCP server is to send back this unicast acknowledge. So discover, offer, request, acknowledge, D-O-R-A, DORA. DORA the Explorer is the mnemonic we use to remember this for the CCNA test. And so at that point, the PC workstation is properly configured with this IP address, a proper type IP address that'll fit on the network, the proper subnet mask. He knows who his default gateway is, so he can relay messages to the other networks. He knows who his DNS server is, so he can look up web addresses and translate them to IP addresses. And he has some sort of default lease time that he'll keep this amount of this IP address before he gives up on it. So every device that connects to a network, yeah, it needs an IP address. If it's going to participate in an IP-based network, it needs an IP address. It needs an address that's proper for that network, not a duplicate address, not a bogus address, right subnet mask, all that other stuff. So what network administrators used to do was assign static IP addresses to everything. What we normally do now is we want to assign dynamic addresses to all our workstation clients. Anybody that brings in a laptop computer or has a desktop student or employee computer, we're going to dynamically assign addresses to those. It doesn't matter what address they get. Just any address that's suitable will work just fine. Now, for our network devices that we control, our routers, our switch management addresses, servers, and maybe printers, we're going to give those static IP addresses. Those things are going to stick around for years. The printer that's in our classroom has been there for over 10 years. That's not going to change. But user computers, oh, they change all the time. They change departments. They change office locations. They don't need any kind of specific static address. It can be any address. And that's going to be some suitable IP address that's within that range of the IP subnet that's been assigned to that room or that floor of an office building, something of that nature. So administrators usually use a network server to be the DHCP server. For example, all the network servers, doesn't matter whether they're a Microsoft server or a Linux server, we can very easily set these up as a DHCP server using some sort of graphical user interface. Pound for pound, Intel-based servers are cheaper than Cisco routers, because Cisco routers and switches are built specifically to move packets quickly. Now, it may be in a small branch office environment where we don't have a dedicated server. Maybe we do want to use a Cisco router to be the DHCP service, so I don't have to put a server in there. So, for example, at home use or small business use, your home router, your small SMB, small medium business size router, that we might use the DHCP services in that, just like you do with your home router. You don't have to. You're not expected to buy a server computer and set up at your house just to hand out IP addresses. So here's the DHCP methods. Manually, no one uses this. Automatic. DHCP assigns a permanent IP address to a client with no lease period, maybe for a server, but I would rather statically assign it. So this is not in very common use, but this is what everybody uses. We're going to use the dynamic feature. We're going to allow the DHCP server to assign or lease for a certain period of time a suitable IP address to all our client machines. In other words, all our employee PCs, all our student PCs, all of the devices that people bring into the network that are Wi-Fi attached, like tablets and phones and laptop computers. And they can get this client IP address assigned to them for some limited period of time. The administrators and upper management decide, is it 1 day, is it 3 days, is it 2 weeks? Typical period is a week or two, so that if someone goes on vacation or they leave the company, their address will be given back to the pool of addresses that can be used, and it won't be hogged forever. So this is a client server type of a thing. Okay, this is not peer-to-peer. This is a client server that the client machine requests. Okay, clients request services and servers fulfill these requests. The client requests a suitable IP address. The server looks at his list of available addresses that have not been allocated right now. He knows what addresses he has, what bank or pool of addresses he has to work with. He knows which ones have already been given out. And when someone asks for a new address, he'll give them a new address that's in the list, and then, well, it's been allocated to somebody. I shouldn't give this to somebody else, because we don't want to commit the cardinal sin, the venial or the mortal sin in networking of assigning a duplicate IP address to 2 different devices. That's going to cause problems on the network. So the client connects, machine connects, the server gives them a suitable address, make sure it's not duplicate. We have a couple of methods we can check to make sure that no one has, there aren't some rogue device on the network that's the same address, so that would create a duplicate address problem. So the device connects to the network until that lease period expires. 1 day, 3 days, 1 week, 2 weeks, whatever the administrators decided to do. Now, when you lease an apartment, let's say you lease an apartment for 12 months, and then you decide you're going to stay. So probably about 10th or 11th month, you're going to contact the apartment manager and say, can we sign a contract for another year? I want to stay another year. I want to extend my lease. So PC workstations do the same sort of a thing. During a certain period of time after, let's say it's a 1 week lease, on the 5th day or 6th day, the host machine will contact the DHCP server and say, may I extend this lease? I'd like to keep this IP address. So that way it won't be returned to the pool and some other device could use it. Now remember, it doesn't really actually matter what IP address a workstation gets. Client machine doesn't care what specific address he gets. It doesn't matter to him. Any one of 200 different addresses would work on a typical /24 network. So he can choose whatever address he likes. And if he happens to get another one tomorrow, it really shouldn't bother him any. It should work just fine. But if he happens to go on vacation for 2 weeks, or he turns his machine off and leaves the company, eventually that address will be given back to the address pool and some other device can use it. So here's our 4-step process. DHCP discovered. The client machine turns on and sends a broadcast message. The broadcast message leaves the PC, goes through the switch, and eventually is heard by the DHCP server. And there might be more than one. In a small business, probably just one. So the next step is the DHCP server sends an offer. If there's more than one DHCP server, there would be more than one offer. Now, this is a unicast. What's the difference between a broadcast and a unicast? A broadcast message is sent to the all ones, layer 2 and layer 3 addresses. It's sent everywhere. It's flooded everywhere. The server now knows what the MAC address is of the client. When the client booted up, he had no idea what he did. The only thing he knew is what's his own MAC address. He doesn't have any idea what his IP address is going to be today. He doesn't have any idea what the IP address or MAC address of the server is. So he has to send it out as a broadcast. But once the DHCP server on the left hears this broadcast from this guy, he now knows the MAC address of the client, and he knows his own MAC address, and he can send this back as a unicast message. So the client machine sends a broadcast message back saying, okay, I request to use your one. In this case, there's only one DHCP server. If there were 2 or more, he would send it back to the one that he wanted to use. If it's so he says something about it's an acceptance notice to the selected server and an implicit decline to the other servers because they didn't get the acceptance. This is also used for if you renew your lease. And then finally, the DHCP server sends back the selected DHCP server. There's more than one. Otherwise, if there's just one, the selected server, DHCP server, sends back the message back to the client machine and says you are now authorized to use this particular IP address, this particular subnet mask, all this other information that we normally send, that we would normally have to statically configure on our workstations. So 4-step process: discover, offer, request, acknowledge. D-O-R-A, DORA the Explorer. There was an old protocol that DHCP is based upon. It was back in the days when we had, for, I don't know, 20 years ago, 30 years ago, there were diskless workstations. They didn't have a disk drive in them at all. And they were popular in large corporations or places like in the defense industry where, like if you worked at General Dynamics or LTV Aerospace or something, we didn't want to put a disk drive in the computer because you could be Boris or Natasha and you might slip a disk drive in there and copy a work, a blueprint and take it back to the Russians. They would also shoot hot glue in all the USB ports so people couldn't connect a USB device, like a flash drive to it. So these devices would boot up, and a bootstrap protocol, BOOTP server, would give them an IP address, and then they would go and download the Windows operating system off a server and boot up off that server image. So this used ports 67 and 68, UDP, User Datagram Protocol, no positive acknowledgement or retransmission, so slim and fast. But the BOOTP was very clunky. You had to have someone collect all the MAC addresses of all the individual workstations, write them down, type them into a table, and manually assign an IP address to each individual one. So DHCP took BOOTP, and it's kind of BOOTP on steroids. So BOOTP, I didn't have to do any static mapping anymore. I just tell the DHCP server, use everything from 192.168.1.100 to 255. 254. 255 is broadcast. BOOTP was a permanent assignment. DHCP is a lease for a configurable time. BOOTP only supported the 4 big configuration parameters. What are our 4 most important parameters on an IP-based device? The IP address, the subnet mask, the default gateway, and the DNS server or name server. DHCP server supports over 20 different things that you might want to use in your company. So it's much more flexible. So this is in the little packet of information that's sent. This is the information that's sent back and forth. It tells us what's the client IP address, what's the server IP address, what are the options. So we can tell things like, oh, what's the DNS name, what's the Windows Internet Name Service name. We can add all these extra functions. So it's very flexible. So here's what we're going to do when we configure a Cisco router to be a DHCP server. This is not, now when we configure a Microsoft, now probably in any large company that's more than 100 people, there's a dedicated Microsoft server. And we're going to use that. It's going to be the DNS server. It's going to be the DHCP server. We'll configure that Microsoft server to do this with the graphical user interface that's on that Microsoft server. So if you take our Microsoft server class, IT and W1454, I think is what its number is, you'll learn how to do that stuff. In a smaller company, like a small branch office, we might use our Cisco router to be the DHCP server, just like you do at home with, you probably don't have a Cisco router at home. You probably have a home router that's Linksys or something like that. So we're going to configure the Cisco router to be the DHCP server. It's going to cost us some CPU cycles and processing capability on that small branch office router, but there's probably only 5 or 20 people at that branch office, and it's not going to be a problem. So here's what we're going to do. First of all, we have our IP address that we planned for at that location, and we're going to reserve some addresses that DHCP should not allocate. So if we have maybe printers or a switch, the management IP address for the VLAN on the switch, if we do have a server there, the router interface itself, like it's probably going to be 192.168.1.1 is probably going to be the first IP address is typically given, traditionally given to the router port. That's the default gateway for all our devices. So we're gonna enter a command that says don't use any of these addresses. Step 2, we're going to enter some commands that say create an IP DHCP pool, and let's say we're going to create a pool for the network 192.168.1.0. We're going to create the pool and name it. You can use any arbitrary name you want to. Cisco best practices is use capital letters, all uppercase letters for your name, for your pool. And then in step 3, we're going to configure the specific task for that pool. We're going to identify the network. So the router will search its interfaces, any network interfaces that are part of that network. He'll start listening for requests and start granting requests out those interfaces. We're going to tell it what the default gateway router should be for all those workstations. We're going to do the DNS server. We're going to identify all that stuff when we set up the server. And I'm going to illustrate that in the packet tracer. On by default, on all versions of Cisco iOS is supported. If I don't want it running, I can type the command from the global configuration mode, no server DHCP, and they'll disable the service. If people are relying on my service, they will no longer get renewals and they will no longer be able to get stuff in the morning. If I want to turn it back on again, which is the default, just type the command server, service DHCP, and that'll turn it on by default. Okay, now let's go to this step 1. I want to exclude some addresses from the pool that will not be used. So I'm going to go to the global configuration mode and enter the command IP DHCP excluded address, and then I'm going to put the low address and the high address. For example, I might say IP DHCP excluded address 192.168.1.1 through 192.168.1.10. So that way, the next available address that he can actually give out would start with 11, and that would give me I will, reserve 10 addresses for network devices. Okay, next of all, I'm going to actually create the IP DHCP pool, and I'm going to type from the global configuration mode IP DHCP pool and make up a name. I'll use TCC, for example. The prompt will change to a new magical prompt we've never seen before, a sub-global sub-interface or sub-global configuration command, config-DHCP. Now, we've seen config-IP when we do the IP address on the device. We see config-line when we do the passwords. This will be, at this point, we're going to actually start typing the individual configuration commands for this DHCP server. Well, the first thing I probably want to do is what network? What network should he assign addresses for? So I might type the command network 192.168.1.0 space 255.255.255.0. Now, some versions of the iOS will actually tolerate you typing in, oh, wouldn't it be nicer to type /24, then 255.255.255.0? So that's one place where you're allowed to do this. So what that command is going to do is look around the router and try to find any interface ports on that router that are up and have any network that's in the 192.168.1.0 network, and use those interfaces for the DHCP processes. Listen for requests, grant addresses. That's also the pool of addresses that the DHCP server will use. So if I said 192.168.1.0 space 255.255.285.0, there means there's a pool of 256 addresses that he will use. Now, of course, he won't use the .0 address because that's reserved for the network function. Of course, he will not use the 192.168.1.255 address because that's reserved for the broadcast function. Now we can configure a specific task. Well, of course, we need to specify the default gateway. So that's traditionally the very first address. In our network, it's probably going to be 192.168.1.1. Typically, only one of these will be required. We probably need a DNS server address. The DNS server address might be typically for home users. That's your home router address, because he sort of acts as a man in the middle for this. If you don't like your ISP's DNS, some cable companies play fast and loose with their DNS servers, and if you mistype a name, they give you targeted advertising. So there are some other DNS server addresses out there that you can use, like Google's 8.8.8.8. My particular favorite is the Quad9 project, which will filter a lot of malware sites that might try to, take over your computer, and that's easy to remember. That's 9.9.9.9. So just set your DNS server address to that, to whatever you want to do. Use your ISP, or you can use Google, or you can use Quad9. WINS is an old network protocol for Microsoft, what we laughingly call them down-level clients. You've got an old client machine. Maybe it's a doctor's or a lawyer's office. They never upgrade. They're too cheap. They've got an old Windows 95 machine that's or an old XP machine that's using WINS, Windows Internet Name Service. That's the 16-character limit. There used to be a thing in the Windows computers called the network neighborhood, and you would see all the employees in your group, and you would see maybe server -1 would be the network server, the file share server for that company. So probably you won't use this command much. This is kind of an old command. You might use the domain name command. On our machines at TCC, they put the domain name, tccd.edu, tccd.net, all those domain names that we use. The lease time, by default, it's going to be 24 hours. We can change it to any time we want, and I would not recommend infinite, because that way the address will never be given back. If it was a server or something, you might want to do that. So some commonly used times might be, a week or 3 days or 2 weeks or something of that nature. So by default, it'll be 1 day. Now, a trick here is if you change ISPs and you have to change your IP addresses within your company, you can set the lease time to 1 hour or something, and then everybody's address will quickly expire, and then you can give them the new addresses that you're getting from your new service provider. Okay, so here are some commands that are not commonly used, like the netbias type. We're not using the old netbias stuff. Those, just for your information, there's other parameters that are available. Now, let's look at our problem about what if somebody has set up a rogue machine on the network and it was statically configured to an address that's within the pool, and the server doesn't know that. He didn't hand out this address dynamically. So as a form of insurance, when the DHCP server proposes to give out a particular IP address to a workstation because they've asked for a new lease, the DHCP server is going to try to ping it twice. So if the ping is unanswered, if I try to ping something and I don't get an answer back, it's probably not present on the network. And you can reconfigure this if you want to. Okay, let's look at the actual configuration on a router here. We've got a router it's not clear. It's kind of behind the we're going to see in a minute the full thing here. There's a router R1 at the top of the screen with 2 Ethernet interfaces. So he's got a 10 dot network and an 11 dot network, and he's being a DHCP server for both of them. So the first thing we're going to do is exclude the addresses from the 10 dot network we don't want to be given out. So they've excluded the first 9 available addresses and the last available address. And then for the .11 network, he's done the same thing. He's excluded the first 9 addresses and the last address. And then he's created the command IP DHCP pool LAN pool 1 for the first interface and LAN pool 2 for the second interface. So the first interface is for the network 10.0. The router's actual address here is 10.1. That's the default gateway for everybody on the left-hand network. The second router is 11.1 default gateway for everybody in the second network. So they define the default router name, and they have a default span name, and they probably would have a DNS command here as well, because everybody needs a DNS server so they can look up web names. You'll have to type in IP addresses. Okay, let's verify this. Show IP DHCP binding will show us what addresses have been handed out. Show IP DHCP server statistics will show us some numbers about how busy the server has been. Show IP DHCP pool will show us, well, what are the range of addresses, not just the ones that have been handed out, but all the ones that are available or have been handed out on this server. And now, a word about debug. Debug is very dangerous, but sometimes we have to use it to track down problems. Debug IP DHCP server events will show dynamically. Now, when you type a show command, you get the output on the screen and it's not updated. When you type a debug command, he constantly puts something on the screen whenever something happens so you can see network activity as it takes place. So if I type debug IP DHCP server events, I'm going to see quite a bit of activity as addresses are allocated and given up and so forth. The problem with debug is it's very intrusive on the router's CPU cycles, on its processing capability, and you should only turn it on for a brief amount of time to troubleshoot and solve problems and turn it back off again. Because a router that's already fairly busy, if you turn on the debug process, it'll start dropping packets. So watch out for turning on debug during business hours on a production machine in the real world. You can do this in a lab all you want to. It's not a real device that's going to inconvenience anybody, another thing. But just watch out for debug. Best practice for debug, only turn it on for the amount of time you need it. Do your troubleshooting, learn what you need to learn, and cut it off again as soon as possible. Okay, now let's look at about the example of, remember when that PC1 and PC2 sent out their broadcast messages for the DHCP server? So the broadcast goes to the switch, it's flooded to the router, the broadcast from the second PC is flooded to the switch, it goes to the second router. Wait a minute, routers block broadcasts. Routers do not pass broadcasts. Oh dear, now we can't get to the DHCP server that's on another network. Well, PC2 is in good shape because the DHCP server is on his network. His broadcast will reach the DHCP server. What about the poor PC1 on the first network? How do we get his broadcast all the way to that server? So what we're going to do is do some smoke and mirrors and magic tricks, and we're going to take that broadcast frame that came out of PC1, and when it's encountered by the router, he's going to convert that broadcast to a unicast. He's going to change it from the broadcast address to a specific IP address that we have told him, namely the actual IP address of the DHCP server, which could be upstairs, or it could be, in our case, it's back at the Trinity River campus. It's not here on the South Campus. So now it's no longer a broadcast, it's a unicast. It can go through as many routers as we want to. The DHCP server will hear him. Remember, he sends back a unicast, so his replies survive the return trip, and the PC1 will get an address allocated to him. So the broadcast is sent out from the PC. The router says, sorry, no broadcasts are allowed to be forwarded. So we're going to program that router to convert the broadcast to a unicast. Relay the DHCP broadcast to the DHCP server. All we have to do is go to that interface port that the lonely workstation that's separated the different broadcast domain from the server and put in the command IP helper address and put in the actual helper address of the DHCP server. And now he can get his server addresses, even if the server is in another building or back in another site. It'll work just fine. Okay, there's some other services here that are also broadcast-based services. If you want to relay them, you can do them as well. Nobody uses any of these old base services except DHCP. So this is kind of archival stuff, legacy stuff that nobody should be using anymore. We're not using time anymore. We're using NTP network time protocol. We're going to get that in the next course after Halloween. So I can use this helper address function, and I can actually tell him to only use, I probably want to use him to only use, in this case, maybe I want to use DHCP and simple network management protocol. Stand by, I'll check the roll here. So in this case, I would allow simple network management protocol and DHCP, and I would turn off all those other protocols I don't want because they're all on by default. Okay, warning, Will Robinson. There used to be a CCNA objective called Security Device Manager, which was a GUI setup utility for the routers. Like home routers, they always have a GUI setup thing. So for several years, this was a CCNA objective. You had to know how to use the Security Device Manager. This is so confusing. Now, SDM means Switch Database Manager. Remember, we had to go into our switch and turn on the IPv6 function? Otherwise, it was IPv4 by default. So this is no longer required. Okay, now we're ready to talk about the same thing, but what if it's for IP version 6? Now remember that when they started with the IPv6 stuff and they started rolled it out officially around the year 2000, it was the zero config philosophy. Everything should work without us having to configure anything. So instead of the piece, this way, when an IP version 6 PC boots up, PC1, he sends out a message, a router solicitation. I need to find out who my default gateway router is, and I need to get some information from it. What is my network, for example? And then the router will respond with a router advertisement, RA, and he'll tell them what that is. So that's the basics of the communication. Now, one of the things that the client machine must do is make sure that there's no other workstation. He's going to, the PCs, the IP version 6 devices can either just make up an IP version 6 address completely out of nothing, or they can take their MAC address and sort of slice and dice their MAC address. And that should guarantee uniqueness because all MAC addresses are supposed to be unique. So the router sends out a router solicitation message. In the purple part, the workstation sends out the router solicitation message. The router responds with, here's your network prefix. Here's some other information. And so the workstation now says, well, I can make up my own global address using the proper prefix. By the way, I wonder if anybody else is using that same address, because older machines, older operating systems would tend to use the slice and dice the MAC address method. Newer ones just randomly generate nothing. Now, if I gave you 64 bits, 2 to the power 64, that's like trillions and trillions and trillions and trillions. What are the chances of your PC making up the exact same address as any other PC? It's like there's more chance you'll be hit by a meteor. But just in case, we're going to use DAD, duplicate address detection, and make sure there's no other duplicate addresses. This is similar to the IP version 4. He would try to ping the address first and make sure no one else has accidentally using it. Okay, so DHCP 6 has got 3 different ways it can be set up with. We don't actually need to set up a dedicated server if we don't want to. We can use the method called SLAAC. Cut me some slack. I want to just use the information in the router advertisement message that he sent me. The second method is stateless DHCP SLAAC, use some of the message from the router that says, oh, I'm your default gateway and this is your network prefix, but go to a real DHCP server that's been configured on the network and he'll give you more information like what's a DNS server, things like that. And then the third option is don't use anything the router gives you, go straight to the DHCP server and get everything from him, which is what we did in version 4 anyway. So here's the SLAAC option. This is pure zero config, no server required to be set up. So the PC is going to send out the router solicitation message, and the router will send back the advertisement saying, use this network prefix. And just if you don't relay everything to me, I'll take care of it for you. Someone has to configure the router to have connectivity with the rest of the world. The stateless option says, oh, now look, we have to actually buy and configure a server. The PC is going to send the message, the router solicitation message to the router. The router will respond with a router advertisement saying, I'll give you a network prefix, but go to the DHCP server for the DNS information, things like that. And the third option is the PC turns on, he sends back the router solicitation message to the router. The router says, can you take your candy ass problem down the hall and go to this DHCP server over here, and he'll give you everything that you need. So those are the three options with the IP version 6. So we've looked at this advertise and solicit stuff, and I'm going to skip to the verification. We can verify this, show IPv6 DHCP pool. Most of the commands that are on the routers that are show IP something, there's a show IPv6 equivalent. For example, show IP route shows the routing table for IPv4. Show IPv6 shows the IPv6 routing table. So we had a command show IP DHCP pool and show IP DHCP binding. Now we can see the same thing with the IP version 6. And there are some very dangerous debug commands that we can use as well. Watch out for debug. It's quite dangerous. So only use it for gathering information and then turn it back off as soon as possible. Okay, redundancy. First hop redundancy is our idea that here's the problems with here's a PC, and he's got one default gateway. Okay, here's his workgroup switch, and here is a multi-layer switch. Oh, I hate that term. This has been configured this default gateway for that. It's got a supervisor module and it's a router on a blade. What if that router crashes? What if someone digs up that wire? Well, he actually has a redundant connection to another switch, another router. What if we configure R1 and R2 to talk back and forth to each other, and they can sense when one or the other has failed, and the one can take over when the other one stops working? So this way, if I have a router failure, that's a single point of failure. If I have two routers, oh good, I have redundant connections. We have spanning tree protocol. We may use fast ether channel to give us more connectivity. So this gives us an alternate default gateway in case something goes wrong. So what we're going to do is have a virtual router. We're going to configure multiple routers, and they're going to, I'm going to call this a ghost address. They're going to actually have real physical MAC addresses and real physical IP addresses, but we're going to configure a ghostly MAC address and a ghostly IP address that's going to be what all the PCs, which they can't tell the difference, that's going to be their default gateway. So we're going to configure this ghostly virtual router as a default gateway for all the workstations on this particular subnet. And the host machines will use ARP. They'll ask the ghost MAC address, what is ghost IP address? This is virtual address, so they'll use that. And that way both routers can take over the job, and one can do the job and the other one can be on standby, or there's some other protocols where they both share the load. And that way everybody's always connected. So this is a mechanism for determining which router is actually going to forward the traffic. There's going to be an active role and there's going to be a standby router. So at the CCNA level, all we are going to use is one particular one, HSRP. So if the main router actually fails, oh, we've got a virtual router that will now take on the new duties of forwarding everything to the rest of the company. And they sort of send heartbeat messages back and forth. The virtual routers send heartbeat messages back and forth so they can tell, oh, he must have crashed. He's not responding to my hello messages anymore. So I must take over now. And they do it very rapidly. So our options are our hot standby router protocol, which is Cisco proprietary. There's a version for IP version 6. Virtual router redundancy protocol is not proprietary. It's not proprietary to Cisco. It works with everybody. And there's a version for IP version 6. And then gateway load balancing protocol is the Cisco proprietary version, and there's one for IP version 6. And remember our old internet control message protocol? That was our mechanism for ping, echo request, echo reply. It's got a lot of other jobs. There's about 20 functions in ICMP. So ICMP allows routers to discover, or host machines to discover routers. So here's the only one that is in CCNA objective right now: hot standby routing protocol, and for one for IP version 6. So this way we've got a standby router and a backup router, and the standby device is going to take over very quickly if something goes wrong. So what we're going to do is we're going to configure our routers with a priority number. We used a priority number earlier in our spanning tree protocol to break the tie between two different interfaces. So whichever router has the active higher priority number is the active router. Whichever router has the lower priority number is the standby router. The standby router hopes for a palace coup to occur so he can take over. He wants to be the boss router. He doesn't want the other one to be the boss router. R2 doesn't like R1. But he has to wait for R1 to fail. He'll know that R1 is still operating because he's going to hear those heartbeat kind of like hello messages from him periodically. When those messages cease and he has crashed, R2 says, oh, joy, I get to take over now and become the active router because the active router failed and I'm now on standby. I'm going to do the job now. By default, these priority values are 100. How about tie breaking? Well, since they're both default 100, whichever router actually has the actual IP address, he'll become the active router. So in our case, the router 2 actually had a higher IP address. If we had not changed the priority values, he would be the active router, and R1 on the left would be the standby router. Do you remember that we had all these states with spanning tree protocol where we were listening, we're learning, we're forwarding, we're blocking? So with HSRP, there's some similar states. They go through a state where they have an initialization phase, they learn about other routers, they listen for other routers' virtual IP addresses, and then they start sending hello messages back and forth between the other routers they've learned about, and either they are active or they are standby. One router is active, the other router is standby. So every 3 seconds, I should hear this hello packet from the other router if I'm the standby router. The standby router, if I don't receive a hello packet for 10 seconds, I'm quickly going to take over. You can lower these settings if you want to, but it's going to cause increased CPU utilization processor time on the router, so don't set it too low. If you're a CCNP guy, you might have a good reason for doing this. Okay, now let's see. I need to stop sharing this, and I need to share this. Okay, so you should be seeing some packages here. Okay, so let me see if I can I minimize this so we can see. Okay, so we have a PC, we have a switch, which is unconfigured, completely unconfigured. We have a router. I'm going to configure the router. By the way, A switch can be a DHCP server too. If we have time, I'll try that. Now looking at our PC, it's set for DHCP. What address is it? I didn't mention this. Oh, I should have mentioned this. What happens on a PC workstation if the DHCP server cannot be reached? Well, it temporarily assumes a sort of a working address, limited connectivity. This is the /16 address 169.net.254, and they take its net BIOS name and hash that to get the last two numbers. So this PC workstation that's not in communication with the DHCP server. Well, look, I haven't even done a no shutdown on the port yet. It could possibly do it. Okay, so I'm going to go back to the router, and let me do a little basic configuration on this router and see if we can get that to grant an IP address to our workstation. So I'll go to the privilege exec mode, and then the global configuration mode. And the first thing I'm going to do is configure the interface port. So interface gigabit Ethernet 0/1. And how about an IP address of 192.168.1.1? Do the no shutdown command. And the port on the switch is still orange. It'll turn green in 30 to 50 seconds. And it'll take me more than that to do the rest of the configuration. Okay, I'll go back to the global configuration mode. And I'm going to do IP DHCP excluded address. And I'm going to exclude 192.168.1.1 through 192.168.1.9. I'll do like I did in the slide. So we're reserving the first 9 addresses for the router and the switch and any server we might have at this location. Now I'll do IP DHCP pool, and I'm going to call it TCC. Capital letters is good practice. Now, what can we do from this layer? We're at DHCP config. Well, the first thing I'm going to do is set the default router. What's our default router? 192.168.1.1. How about our DNS server? I'll use the quad 9.9.9.9.9. Oh yeah, I should have done the network first. Network 192.168.1.0, 255.255.255.0. And it should be operating now. We're in the green here. I'll do a show IP interface brief. Is it up and up? Looks like it's up and up. Let's go back to that PC. And I'm going to go static DHCP and see if he gets an address. Oh, look, he picked up the 192.168 address. 1.10. It worked. Oh, good. We excluded 1 through 9. He picked up 10. So in theory now, if I go to the desktop of the PC, he should be able to, if I do IP config, I should be able to ping my default gateway. And that works fine. Okay, now let's just for fun, let's do this on the, I'm going to go back to static here to clear it out. I'll go back and turn it back to DHCP. I'm going to go to that router, and I'm going to, why don't I just go to configure terminal and interface, interface gigabit 0/1 and do the no shutdown command. That'll shut down, no communication. And let's configure our switch to do the same sort of thing. It's the same commands on the switch. Okay, so here's our switch. Here's our CLI. It's completely unconfigured at this point. So if I do show IP interface brief, you can see that port 6, well, it's kind of hard to see here. It scrolled up so fast. Port 1 is down because I turned off the router, so port 1 went down. Port 6 goes to the PC. It's up and up. But there's no IP address on the switch yet. So I'll go to the global configuration mode, go to configure terminal, and let's go interface VLAN 1. Let's use the default VLAN. No security in this. It's a demo. And I'll go IP address 192.168.1.2 because the router was 1 and no shutdown on that management address. Okay, now let's see, can we actually configure this switch to be a DHCP server? And we can do it on our real machines in the lab. They can be a little mini DHCP server. They can do a little bit of function because they have a little bit of layer 3 functionality. They're not a full-blown $20,000 or $1 million switch, but they can do some stuff. So I'll go to the global configuration mode and IP DHCP excluded address 192.168.1 1, and this time I'll make the number different so we can prove the switch did it and not the router. .168.1. I'll do 11. That way, our workstation should come in with a 12 if this actually works. Configure terminal, IP, DHCP, pool. I'll call it South Campus instead of TCC. Okay, network. What's our network? 192.168.1.0, 255.255.255.0. Default gateway, 192.168.1.1. DNS server, quad 9. Should be enough to do it. Let's go back to our switch, to our PC. Can you see the PC? Yeah, it's flickering, isn't it? Let's go back to DHCP. Give me an address. That's not right. Did I exclude this properly? Did I not do excluded address? Show run. It must be a anomaly in packet tracer. It should have given me the address. But you can see that the switch is actually acting. Well, let's see. Can we ping? Can we ping? We'll go to the PC. We'll go to the desktop. Config. What is IP config? Oh, IP config reports the correct address. Look, it's 1.12. And can I ping the switch now? 192.168.1.2. Start pinging out, timing out, and then it should work just fine. And it works just fine. Maybe first and second requests usually fail. Okay, so I'll stop sharing this. Go to here. Share this. Share application. Oh, I'm already sharing. I have to stop sharing this. Share application. So let me double check the role here. Got him, got him, got him, got you. 1, 2, 3, 4, 5, 6. Okay, guys. So I've completed the PowerPoint presentation for the topics for today, and then Thursday we're going to do. It's going to just be a lab on DHCP version 4. I'm not going to have you do the lab on version 6, and you'll have to do the lab on the router redundancy stuff. So I'll see you guys Thursday, and thanks for coming and sharing the lecture with me today. Looking forward to see you guys later on. I'll hang around for a second in case anyone's got any chat messages.